Okay, so welcome back everyone. So till the last session we had been talking about, we first did random variables and then we went about trying to understand the fundamentals of reinforcement learning, where we studied the bandits algorithm. We saw several things like states, actions, and rewards. But now, till now, we used random variables for bandits. We used conditional expectations and so on. But as I had promised you in the first session, that we will have to, that the agent takes an action and state changes in the environment. So my point to all of you is, so if the state is changing in bandits, it did not happen. Right? Can you hear me? So just for confirming.
Yes.
Okay.
Yes.
So in bandits, it did not happen because there was only one state. But now we have to go past it. Say, for example, the example I gave you in the first day, in a tic-tac-toe game, there are so many states that we saw. With every action, the state transition to a new state. So to understand that, we'll have to take a full session today on understanding what a random process is. We have understood random variables, random vector, that is joint variables, but we have not understood what is a sequence of random variables in a meaningful fashion. So what we'll try to do is, with all our probability knowledge, we'll understand random processes um, and Markov chains, because Markov chains and Markov decision processes would be the central theme of all our future discussions. Okay, so what is a random process? So I have written a mathematical definition. You can go through it once you get the notes in hand. But the basic idea is, a random vector process is a map from, again, remember what is a random variable first? Recall, a random variable is a map from the sample space to
Real number line.
real number line. Okay, so now I define a subset of the sample space. Okay, right? Which is, say we define this as script X. So you call this script X or something, and then which is a subset of random variables. So random variables need not always be real number line. They can be 1, 2, 3, 0, 1, and so on. So that just for that, I say that the so that it is not a codomain but a range set. I define a tight range set so that X is a map from, first of all, this is a random. Okay. So first here, and then this is a random process. We'll try to intuitively understand this as well, but yeah, so let's understand the mathematical foundations of this. So you say you define a subset of the real number line that is given by script X, and you define something called as the index set or the time set. Index set or time, that is some chronology, right? Some chronology. So I say that it's a map from the sample space to x to the power t. What does this mean? It means that, what does x to the power t mean? Any idea? Script x to the power t mean? Say your script, your time set is 1, 2, 3, and n. So what would be your script? set is my question. So say your x's are a and b. So what is x to the power t going to be? X to the power t means it's a map for between what? What is it a map between? So the best way to visualize it is like x, 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 t times. So what does this mean? For every time point, okay, so you can choose A or B here, A or B here, A or B here, and so on till the end, right? You can keep choosing one of these two functions. So the idea is it's a map from the T set that is 1, 2, 3, n to the X set. Is this fine to everyone? So this can be A, this is the function. This can be B and so on. Is it okay? Oh, sorry, not B. C can be B and so on. Is this clear? So this random process is a mapping from the sample space to this mapping itself. So can we simplify this idea? So this idea says x1 is equal to A, x2 is B, and so on. X capital T is B. So the idea here is it's a collection of random variables, right? This x1 to xt, yes or no? Because they were all mapped from the sample space to the real number line, which is to the subset, that is this is the script space, the space that we talk about, the range space. Any idea? So what I'm trying to say here is this is a sequence. In other words, the random process is a sequence of random variables. That is an ordered sequence. That is x1, x2, x3, and xt. So it's like something like this. Say you are tossing a coin, right? At x1, you get a head. Example, coin toss. Example, 50 coin tosses. So let's take this example and try to understand this. Example, where do I write this? Okay. Example, 50 coin tosses. So can you tell me what would be the random variables be? First of all, tell me what would be the random variables. They would be x1, x2, dot, 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 x50, yes or no? Because you have 50 tosses. Any doubt?
Yes.
And each of these xi's would be Bernoulli p random variable, yes or no?
Yes.
Yes.
Okay. So in other words, you can also write this as this random process, this entire tuple can be written in one go. X is a map from the sample space to what are the two outputs possible? 0, 1 to the power 50. Yes or no? This is what you can write this as. For every index, you will have one output, right? No problem. Everyone, it's clear? You can also name this like T1, T2.
So instead of like mapping to one single random variable, we are mapping to t random variables, right? I can't hear you. Yeah, I can hear you now. I couldn't hear you for so long.
Okay. Sorry, I think there was a network problem. Uh, Yeah, so what I was trying to say is instead of mapping from a single number, random sample space to a single number, you map to a tuple of numbers or a list of numbers. That's what is a random process. So that's why I wrote this notation A to B. This is the function, right? A to the power B function. So for every element in B, you plot it to uh, map it to an element in A. That's what I was trying to include. But if it is a bit difficult for you at the current moment, what we try to understand is it is a sequence of random variables, nothing else. It is x1, x2, x3, x4, x3. So in terms of events, you directly get the entire sequence. But if you see this sequence of events, you can think of it as that the first random variable happened, then the second one happened, and the third one happened, and so on. Is that fine?
Yeah,
Any questions? I'm willing to take. Because once I go into the questions, this will become very simple. But there is the subtlety in the definition of a random process. That's what I'm trying to get to you. Because once you get this idea of a collection of random variables, it's going to be just a very simple thing to go ahead and do. Okay. So let's do a couple of questions. So first question is write a distribution of the random. So if I tell you to write the distribution, so it will be for all the joint distribution for all the say small x t. So what will be the distribution be looking like? People who have attended the joint probability class. This will be probability of x1 less than x1, x2 less than x2, and so on. This is exactly the same as what we had done for two variables, right? It's for t variables now. Is it clear? So this is the intersection of the probability of the intersection of xi less than x. All the events from I equal to 1 to t. Is this clear?
yeah,
Fine.
okay.
So in our class, we had written this as probability of intersection of t equal to 1 to t, xi inverse minus infinity to xi. This is how we had written because we had defined the random variable again as a map, xi to be a map from the sigma to the real number line. So for anything on the real number line, we took the pre-image to define the events. Just reminding you. Fine. So now this is the first question is done. Okay. And X is also called the state space. Just I was just trying to recall the term. So it's called the state space. So you're seeing that the states are coming up over here as well, because these are the states that the random process can be in, right? So we'll come to this. We'll understand them in more details. So now I have seen that f of x1 dot 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 xt is the probability of the intersection of the events xi to this. So now I ask you this question, if they are independent, if x1 dot 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 xt, this is called an independent process, then what will happen? If x1 to x3 is an independent process, what will happen?
We could product out the
Yes, so we can
individual.
write this as a product. I equal to 1 to t, probability of xi less than x, small xi. So this is pi of I equal to 1 to t, fxi, small xi, right? For independent process, random process. Okay, so this, I hope you get this idea. So what is the takeaway till now? The takeaway is the random process is a collection of random variables in a particular order, x1, x2, x3, and xt. It's like, now let us try to take some concrete examples to understand what it looks like. So now you can look at the notes over here, but tell me, this state space and the index space. or index set. They can be both continuous or discrete, right? State and index, right? So this is this is first of all, let's write discrete, and index is also discrete. Continuous, continuous. Now tell me, for discrete state space and discrete index sets, can you give me an example of a random process? So this is called a, as I have mentioned over here, it's called a discrete sequence. Anything that has the time is discrete is called a sequence. So this is called a discrete sequence. Again, index set, this is called a, so I think I missed labeled. I'll just try to keep the same index over here. This is the index set and this is the state space. Okay. So now the index set I am saying is still discrete, but my continuous, I have a continuous, it's called a continuous sequence. So the first thing is the state space, and the second thing is the whether the index set is labeled or not. There are two things here again. And then if the index set is continuous, it's called a process. Again, process. This is a continuous process, and this is a discrete process. So we will be only dealing with this first case where we have a discrete sequence. Okay. So now let's take some examples of discrete sequences. So discrete sequence would be something like this, right? So let's write this number 1, 1, both states and index are discrete. So it's something like this. Say x1, x2, dot, 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 xt. And each of these xi could be between, say, values v1, v2, vk. Yes or no? Did you understand? These are the random variables. These are the random variables. And these are the values the random variables can take. So something like this. If you count the number of customers in a bank every day. Yes or no? This could be a random sequence which is both discrete state space and index space. Because first day 1, say you have 50 people. Second day 20 people. Thursday 10 people. So 100 people. So yes or no? Any? Okay. So if you've understood, can you give me an example of continuous sequence? I'll just write it. Do I have some space? No. Okay. So the second question is x1 dot 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 xt. So these are discrete time, but each of these belong to say R or some A to B, which is continuous. So can you give me a example of this?
So, being in the realm of banks, we can just say that the amount of money withdrawn on a particular day could be an example.
Great. Amount of money withdrawn every day. Very good. Similarly, you could have, so all the 4 combinations are possible. So we will only discuss 1 and 2 here, where the state space is continuous or where the time index space is discrete, because it will help our lives, and RL also works generally. Introductory RL only works on those 2 spaces. But let's take an example of discrete process. That is, time is continuous. Right? So say t is 0 r plus. time is continuous, but you say the state space is discrete. Can you give me an example?
Number of participants in a Zoom call at a particular moment of time.
Very good. Very good. Number of participants in a Zoom call at a moment. And number 4 could be discrete sequence, a discrete, again, continuous process. This is why this random processes are important, because when we trying to model time series data, it becomes very, very important, both in machine learning and in reinforcement learning. So random continuous process, again, T is say in R plus, and your X again is say between equal to A and B. So this is again, say, level of water in a dam. Right? What is the level of water? How much height of water at a time? These are the few examples that I wanted to convey. Is there any questions? These were like intuitive examples. We'll go to more concrete versions now. Okay. Anyone? Any questions? Okay. Fine. So we'll start off with what is called a random walk. So please tell people to revise this and come for the next class, because after this we'll just do code MDPs, which is Markov decision processes, which entirely depends on this. Okay. In a random walk, what happens is from the, again, it's the same thing I'm going to mention. It's a random walk is a map from the the sample space to the powers 2x to the power n, same. So n here is natural number. So again, T is just indexes, x1, x2, x3, x3 is a countable index set. These, you get a collection of x1 to xn, and you say that you define a random walk Sn as the sum of all the xi's, which is the with a step size, and each of these are called the step size, such that S0 is equal to 0. So it's like something like this. A random walk is walk. Say you have x1, x2 dot 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 xn. At a moment in time, the random walk is given by Sn, which is the summation of I equal to 1 to n, or rather, let's write T xi. Is this fine? Such that, and you start off, say, with S0 as some 0. It's like, for take an example, toss a coin 10 times. Say x is equal to 1 is head, and x equal to 0 is tail. So what would be the, for this sequence, HHTTH, or rather HHTTH, what would be S1, S2, S3, S4, S5, S6? What will be H6?
3.
Very good. So it will be 1 plus 1 plus 0 plus 0 plus 0 plus 1, which is 3. Good. So now let us try to take a concrete example and try to solve that. So in this concrete example, what you say is, say you're playing a game on the real number line, and the players are told to toss a coin, and if it is landing on the head, you move forward 1 unit. That is, x is a Bernoulli pre-random variable. Define a random walk in terms of Sn and x0. Okay, let us try. So the same type of a question. It says that Sn. So let me draw the diagram first. Say you are at a position P or I, for example. So now what are we saying? So with probability P, you go to I plus 1, and with probability 1 minus P, you stay at yi. Yes or no? This is what we are saying. This is because we are tossing a coin. Coin head is moving one step. So what I say is, say xi is equal to, is distributed as Bernoulli P, and they're independent, IID. So your random walk Sn is the summation of I equal to 1 to n xi with S0, which is also equal to Sn minus 1 plus xn. Yes or no? This is also another representation. Many books write it in this form. So you've given the state at n minus 1. So Sn minus 1 is say I. So Sn plus 1 can be I with probability P, 1 minus P, and it can be I plus 1 with probability P. Right? That's what it's trying to say. So we'll come to this in more details, but the first question is, we define the random walk. Now I am told to find the PMF of. 2 is PMF of the random walk. Can you tell me the PMF of the random walk? What is the PMF? Sn equal to K, K less than N, say. 0 otherwise. Yeah, go ahead.
1 minus p to the power n minus k into p to the power k, the binomial.
Binomial distribution. Good. So here we are trying to say, so here Sn equal to K means, as you had pointed out in this S6 equal to 3, it means that, so you have all the n options, n x1, x2, dot, 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 xn. These each can be 0, 1, 0, 1. So there should be k ones and n minus k zeros, as I explained in the first day. So this is p to the power k into 1 minus p to the power n minus k. Now, how many of these such combinations can we create? How many of them can we create? So all permutations of this, so all the permutations, that is n factorial by k factorial into n minus k factorial, that is n choose k. Yes or no? In other words, all such rearrangements such that there are k ones. Okay, I hope this is clear. So let's go to the interesting or the third part of the question. So there's no space here. I'll go and do it at the end. So find the expected time for the random walk to reach a constant n. Okay, so let's just copy this. Okay. So find the expected time for the random walk to first reach a state n. So let us see, this is also called a counting process. When you study probability, you'll see. Called the counting process. What does it mean? Say, I will use x and y axis over here. This is Sn, and say the x-axis is n. All right. So say at time 0, you started at 0. Then at 1, you stayed at 0, which means x1 is 0. Yes or no? Fine.
Yes.
So this is your S1. Say next, another 0 lands. So this is S2. X2 is 0. Now suddenly 1 lands. So you go here. Yes or no? This is your, okay. So x0 and then x3 is equal to 1. So which 0, 1, 2, I think this interpretation is a bit of a problem. Just give me a moment. Okay. So it says that x1 is equal to 0. So I have to write it in under this. X1 is equal to 0. Therefore, you stay here. X2 is equal to 1. So your state 2 becomes, this is your state 2. State 1 is at 0. Is this fine? And then, which is at 1. So again, I am trying to write down this sequence. Say x is 0, 1, 1. Let's say, let us deal with this sequence. 3 zeros and then a 1. So can you plot down the graph for me? So 0, 1, 1. So first x1, S1 is 0. S2 is 1. What is S3 going to be? This is 1, this is 2, this is 3. Tell me, what is S3 going to be? 2, right? Yeah, somebody told me.
2.
Good. S3 is 2 because you can see x1, x2, x3, x4, x5, x6, x7. It stays in 2 until 4. Again, 4 to 5, it stays here. 5 to 6, it stays here. And then it jumps to 3. Yes or no? Correct? At 7?
Yes.
Okay, I made a mistake again. This is 5, this is 6. And at this step, you jumped to 7. Okay, that is 3. Fine with everybody. So now I am asking this question to you that what is the first time in which, so first tell me, what is S? Let's write down the S's. S. Okay, S1, S2, S3, S4, S5, S6, S7. Tell me what is the value of each S. S0 is, S1 is 0, S2 is 1, S3 is 2, S4 is 2, S5 is 2, S6 is 2, S7 is 3. Yes or no?
Yes.
Okay. So now I'm telling you, we want to find that time when the first transition to the next step happened. That is, if I ask you, so first tell me t such that st equal to n. Let's do an example for this. Say t such that s2 st is equal to 2. Is a set. Let us define this as s2 or some set of m2. So can you tell me what is the value of this set? All the time points such that st is equal to 2.
3, 4, 5, 6.
Yeah, 3, 4, 5, 6. This is 3, 4, 5, 6. So I tell you, find out the minimum of the set M2. That will give you the value, right? It's not n. Minimum of this is capital N, let's say, of N. So N2 will be, what will be this value? Minimum of 3, 4, 5, 6. This is equal to 3. Yes or no? Fine. So at 3, you went to 2. So your N2 is equal to 3. Tell me what is N1? So it's trying to see the x-axis. Given the y-axis, it's the inverse function actually. It's 2. And N3 is
7.
7. So the first time the transition happens is going to be marked here. Okay. So I ask you, what is the expected time for number of successes to be n? That is n. To reach a constant n, what is the time that it takes? Can you tell me how to do this? So I'm trying to say what is the expected time for minimum of t such that st equal to n. What is this value? I'm trying to ask you this question. What is the time taken? So that is some nn. Can you tell me how to do this? So first, what do we have to consider? So we have to consider how many ones. First, tell me how many ones do we need to get a success? So see, the last step has to be a success. Yes or no? Last has to be one x, right? Has to be one. Yes or no?
Yes.
So this is say x and n has to be 1. So this is 1. So now how many times did we try is what we have to find out. So all this, everything towards the back of this can be either zeros or ones. Yes or no? Fine.
Yes.
Yes.
Say 0, 1, 0, 0, 0, 1, 0, 0, 0. So how many ones do we need?
N minus 1.
Because at the end of the day, I need total of n ones, right? N ones. But before the time it ends, this is what we want, the ending time. Before the ending time, how many ones are required? N minus 1 ones? Yes or no? There should be n minus 1 ones or not? And some arbitrary k number of zeros. Do you agree? Fine.
Yes.
Yes.
So now, do you agree that this first part can be written as a, what can you write this as? So this is number of failed attempts to get n minus 1 successes. So there are, so not exactly this. So n minus 1 out of k trials are successes. Right? We want this value of k. So this total thing should be k or k minus 1, whatever you want to say, because last one is k. So n minus 1 of them. So I choose n minus 1 from this k minus 1 and then do the same thing, yes or no? Like a binomial distribution, p to the power
Yes.
n minus 1 into 1 minus p to the power k minus 1 minus n minus 1, right? This is p of nn equal to, is what I'm trying to say. So to get, so this is trying to say number of times you need to attempt to get a or n successes. But at the end also we want one success, yes or no? That's why we kept one for the last, because that's where we stop. So you end up getting k minus 1, choose n minus 1, p to the power n, 1 minus p to the power k minus n. Okay? Is this fine?
Yes.
Fine. So this is the PMF. You are told to find the expected value. One you can do is, it's also the negative binomial. What you can do is you can take the expected value with terms of k, but that is a very, very cumbersome process. I can give you a much simpler process. Can any one of you tell me how can you do that? You can define other random. Yeah, right. Yeah, Antariksha.
We can use the linearity thing we used back then for bio.
Yeah, okay. But somebody else asked me. Did somebody else ask me something? Okay. So again, linearity would be is a good answer, but how exactly do you use linearity? Let's divide this into small tasks. That is, you get one success. Do you remember this distribution? That is, get the first success. This was the geometric P, yes or no? Where 1 minus P to the power of n minus 1 into P. This was your geometric P distribution. Yes or no? That is, you get one success. Now again, I say that this is the time that it requires, T1, to get the first success. Then I can just keep doing this, yes or no? T2 n times, yes or no? If I just say my total time is T1 plus T2 dot T small n, yes or no? Do you agree? Intuition clear? So every time I get a success, I restart the every time I get the success, I restart the experiment. So I restart the geometric experiment. That you toss a coin, you keep tossing it until you get a success. Right? So what would be the expected value of T? It would be n into expected value of T1. Again by IID and linearity. So now what is the expected value of T1? The expected value to get the first success. We did this last time. The geometric expected value of geometric P is 1 by P. The intuition is what? So we derived this, and I think all of you had uploaded the solutions to this. So
Yes.
geometric P is, so you say if the probability of getting a head is 0.5. So how many times do you think do you need to toss to get the first head on expectation? 2 times, 1 by 0.5, 2 times at least. That's the idea. If it is very unlikely, say probability of getting head is 0.1. So at least 10 times you need to toss on in expectation to get a head, yes or no? Okay, so this becomes n by p. Any doubts? I guess I could do my best to explain this, but yeah, any doubts? This trick is very, very essential. This is the negative binomial distribution. And we derived it from a random walk. From a random walk. Fine. Okay, so enough of warm up. Now let's go to the crux of the session today, that is Markov chains. This will be very simple, I think, for computer science students, because a Markov chain can be represented as a graph. And also for people doing DSA and things like that. Yeah, let's go into this. So what we'll be considering is there are multiple types of Markov chains. They can be continuous, discrete, so on. But we'll be considering when the state space is discrete and the time space is, the index set is also discrete. Okay, so we'll consider only the first case. So it's called, only in this case, it is called a discrete time Markov chain. Okay, so a discrete time Markov chain of process of order 1 is this. Say your Markov chain again is a random process. Your Markov chain is a random process. Again, recall x1. How many? What can I write? Say you have t possibilities, xt. So each of them can take values of, say your state space is small x1, x2, and k. So each of them can take value between. Tell me. Each of x1 to xk, the random variables collection. Again, Markov chain is a random process, so it's a collection of random variables. It can take a value between. Anyone? They belong to the set x1, x2, xk. So for example, capital X1 can be small x2, capital X2 can be small x5, and so on. Is that fine to everyone?
Yes.
Yes.
Okay, so what does it say is the Markov chain is a phenomenal intervention. It's a phenomenal idea, which is true in like try to true to model every state in life almost. Why do I say that? It's like if you are in a current state, say you are in a current stair, your next state just depends on your current state and not on your past. Right? So the intuition is, I'll just give you the intuition on the story, the philosophy. Your future step only depends on the current state. Future means t plus 1th state. Current state is tth state. That is, if I give you the entire history. So for example, your history for a process is given to be x0, x1, x2, dot, 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 xt minus 1 or xt. This is a history set, right? So for example, I take this entire set and give it to you. Xt minus 1 is equal to say x6 or something like that. I give you the history set of random variables. What is it said is your xt plus 1 given entire history set is just dependent on the previous state. Is this clear? Do you all appreciate this? So it's independent of everything else. Independent of everything else. Is it fine? I'll show you a graphical representation. So for example, at a current state xt minus 1, the transition to xt transition xt minus 1. That's why I crossed this out. Are there any questions? Any questions? Any doubts? Because rest of it is just going to be Markov chains. I'll wait for a moment or two. Before proceeding. Get this graphic in your mind that your current state just depends on, or if your next state depends just on the current state. Fine.
Yeah, it's fine.
Okay, if there are no questions, we go ahead. So the next, the thing that I want to say is just prove this simple equation. Say you have a joint distribution x1. So again, if you are confused, this means any value it can take x0, x1. This is a shorthand for this. In case you are thinking that what is the other writing, this can be written as. Can you tell me? So I am saying you have to prove this that it is a product of all the states. So x0 to x1 to x2 dot 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 xt. So this is just the product multiplication of these probabilities is what I'm trying to say, right?
Yeah, because the up to t minus two events, they would be all independent, so we would be able to product out till then, and then
Good.
won't be able to product out the last two conditional probability. So we need to write.
Can I write this as this by Bayes rule? This is what you're saying. You're producting out, right? This is by Bayes rule. Probability of A given B is the probability of A comma B by probability of B. Here B is the entire set from 1 to T, right? By Bayes rule, I can write that. Okay.
Yeah.
So now tell me by Markov property. This is called the Markov property again. So just to mention the popular uh, nomenclatures in literature, Markov property. So by Markov property, what can I write this as? So the Markov property states that it does not depend anything on the past. So it's independent of all this. It just depends on xt minus 1. Xt just depends on xt minus 1 by Markov property. Okay, fine with everybody. Into probability of x0, x1 dot 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 xt minus 1. Now you get the idea how to do it. Now what do I do with this part?
Probability
Again,
of xt minus 1 given the rest.
okay, xt0 to I'll write in a short for. And then what will I get this as? Probability of xt minus 1
xt
given
minus
xt
1
minus.
given xt minus 2.
Good. And this continues by induction. This will go on to probability of xt given xt minus 1, prob t equal to 1 to t. Right? By recursion, you can write that, right? Till you remain only x0. Fine. Any doubts? I'll wait for a moment. Okay, this is just, I hope if it is clear. So let us go to what is the graphical representation. This is all you'll need mostly for reinforcement learning. But if you are interested to learn more about it, I think in my previous course I had done a lot of random processes. You can go and look at that. But I'll be more concentrating on the graphical methods. I'll give the link of this of that course of that less session in the group and also in the video. Fine. So let's see what is a graphical representation. So graphical representation of the Markov process is again now, as you can recall, there how many states are there? The states, as I was saying, is like x1, x2 is the outcomes. Each xi could belong to the small k states. Yes or no? Right? One of them it can belong to. So your state space, in our case, I am referring to some index 1 to n, small n. Right? So say this is 1, this is 2, this is small. This n, this is small n. Fine. So each of random variable in the tuple x1 capital T would belong to one of these. Again, T also is so T is again discrete. In particular, it is the natural numbers, countable. That is 1, 2, 1, 2, a dot, dot, dot. You can include 0 as well if you want. Natural numbers plus 0. Something. Just basically, it should be countable. That's it. So what I say is, look at this. So the probability that xt plus 1 or rather xt is some j given xt minus 1 is equal to I is say given by a probability Pij. This is how you define. So there are two parameters here given the previous state, the current state. So it's a transition from, so if you have a state I, it's a transition from state I to state J is given by this probability. So it becomes a graph at the end of the day. So what is the dimension of the graph will you get? Can you tell me without saying? If you are doing data structures, all of you, I guess, are doing it. So it's a map, it's a transition from I to J. I to J. What does it mean? It means that, so say you have n states, 0, 1, 2, 3, 4, 5, dot, 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 n. What is this transition going to be? P? Can you tell me?
2, 5.
2, 5. So P 2, 5 is the probability that xt is equal to 5 given xt minus 1 is equal to 2. Good. So now I say that a transition matrix P is a transition matrix. Which keeps all these Pijs. So I have not taught linear algebra this time, but I've done it twice in the previous two cases. I think you all know basics of matrices. That's all there in your +2. So what I say is I just write X train as a transition matrix as a matrix like this. So this is again an n cross n matrix where the rows I is the transition from state I to all other states. Probability of transition from state I to all other states. Right? So state 1, 1, 2, dot, 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 n. This is I1, I2, dot, 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 In. So tell me the entire transition matrix will look like. It's a bit lagging. P1, P2, dot, dot, Pin. So the entire transition matrix will look like P11, P12, P1n, Pi1, dot, 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 Pij, Pin, Pnn, P1n. Yes or no? Fine with everybody?
Yeah.
Good. So now I have a question for you. So now there are problems in which this transition matrix changes at every time. For all our assumptions, we will consider our homogeneous discrete time Markov chain where the probability function is same across the transition probability, the same across all times. Is that clear with everyone? So every time the transition probabilities will be fixed. Okay. Great. Fine. Before we go to the questions, let us try to write down the transition matrix for this graph. Will help me with this? I'll just write it down here. Sorry for the ink use, it's just a clutter. So how many, what will be this matrix of shape of 4 by 4? Yes or no? So again,
Yes.
1, 1, 2, 3, 4. Okay, 1, 2, 3, 4, 1, 2. So now tell me what would be the first row of this matrix?
1 by
From
3, 0, 2 by 3, 0.
is it from 1 to 1 is half?
Sorry, I just saw 2 as 1.
No problem. I think, oh yeah, I changed it a bit just now. So 0. Okay, 2 you say 1 by 3. 2 is okay, no. So 0 1 by 3, right? 0 1 by 3 and 2 by
2 by
3.
3, 0.
So again 0 2 by 3, yes or no? So I am considering this transition and this transition from 1 to itself and 2 to 4, correct? The third row, now from 3 to itself is 3 by 7. 3 to 2 is
3 by 7.
3 by
okay.
7.
And what else is left?
3 to 4.
1 by
Is
7.
1 by 7. And the last one is 4 to 1 is 2 by 5. 4 to 2 is 1 by 5. 4 to 3, 2 by 5. So what are you getting here? So do you see a pattern over here? Can you see a pattern in this matrix?
Yeah, I mean, the sum of every row would be 1 because that's how we define this.
Very, very good. The practice sum of how the sum. So Bij I equal to 1 to n is equal to 1. Prove that. How do we prove it? It's just a one line proof, but just for the exercise. Sorry, it's j, sum over the j's, not i's, because we are summing over rows. Okay, the ith row sum. Okay, yeah, please tell me, how do I prove this? Any idea? Very simple. So what is Pij? Let's go to the definition of Pij. This is P of xt plus 1 is equal to j given xt is equal to I. So now that's all the states it can go to, right? By law of total probability. Law of total probability. This is equal to what? Yes or no? Proof is Pij I equal to 1 to n is nothing but it's fine.
Yeah.
This is because given a state, if you want to understand, just look at this. I have to go somewhere, right? You have to go somewhere. P1, P2, dot dot dot, PI1, PI2, PII, PII. You have to go somewhere. So the sum of all this will be equal to 1. Right. Now let us see a few properties and results and then go to questions. Okay. And we'll be deriving these properties as questions itself. So let's first see, say our initial distribution of a Markov chain is given by, so pi 0 is the initial distribution, which is x0 will be for all I in the state space 1, 2, dot 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 n. Okay, so which 0 is this? So you have that P set that is 0, 1, 2, n. So I'm saying the x0, the first random variable in the sequence. Whenever you are confused, write down the sequence first. The first random variable in the sequence is x0 has this distribution, that is pi 0, 1, pi 0, 2, dot, 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 pi 0, n. Yes or no? There will be a probability if you draw the histogram. They will have some probabilities of being like one of the states, 0, 1, 2, and this is say pi 0 of it. Fine? To everyone? Everybody will, each of the states, that is 1 to n, that is in the state space, would have some probability of being in that state. So my problem to you is, what is going to be p of the pi of 1 of I? Can you tell me pi 1 of say 1, not I, but j, of an index j? What is the probability that pi 1 is j? What means that probability of x1 is equal to j. How do I find it? Can you help me to find it? That is, you make a transition. One transition is made. Transition is made by the Markov chain. That is, now you get x1. What is the probability that x1 is one of these? So if you're anyways forgetting, there are n states. So I say one of the states, the probability that it being states at this time. Yeah. Tell me, how do I do this?
We,
Any idea? Whenever
P
I
of,
don't, yeah.
it would be Pij into pi 0 of I.
Okay, I understand that, but I want not the final outcome, but how do we do this is what I'm trying to say. But I see this is a marginal whatever distribution I have. But I don't know any idea about it. So what ideas do I have? What is known to me first? I know is
Previous state.
exactly. I know the previous state. So I know, and I know this distribution. If this is j, this is I, this is p, as you were saying, pij. So I can write this as, can I write this as the law of total probability? See, once you are able to do this, as Antariksh told me, you can write this immediately. The immediate writing is a bit of a problem to start at. So when it's immediately, if you're not able to write immediately, what you try to do is you represent this as a law of total probability. Xy equal to j, x0 equal to I for all I between 1 to n. So now once I get this total number, I just do Bayes rule. Or I do conditioning, whatever you like to say. Do you agree? I know all these terms. This is law of total probability, and this is conditioning. I know all these terms. This first term is, as Antariksh was telling me, Pij, I equal to 1 to n. And the second term is pi 0 of I. This is just pi 1 of for all g. So now I can write this actually in terms of a matrix. See, by your class 11, 12 maths, if this is your pi 0, 1, pi 0, 2, dot, 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 pi 0, n, and you have a matrix p11, p12, dot, 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 pi1, I that 1j, dot, 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 p1n, pn1, pnj, pnn. Do you see that each of this element, this is your pi 1, 1, pi 1, 2, dot, 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 pi 1n. Why do I say that? Say the pi jth element, pi 1 of j, is the, how do you get that? You get this, you do a combination of this column, yes or no? So you multiply pi 0 of 1 into pij plus pi 0 of 2 into p2j and so on, yes or no?
Yes.
Just the matrix multiplication. I take this and I just multiply it with every row. So this is a 1 cross n matrix. This is a n cross n matrix. I get a 1 cross n matrix again. Fine. So your entire thing can be written as pi of pi1 and pi0 into p. So now, if I tell you, give me pi2, what will you write this as? Since it is since homogeneous, let's write pi2 as by induction. Can you write this as by induction? Anyone? Pi2, I can write this as pi1 into p.
Yes.
Very good. Similarly, I can write pi k as pi k minus 1 into p. So now just do recursion. Put the value of pi1 here. So it becomes pi0 into pi0 p. What did I write? Yeah. P, sorry. Pi0 p into p, right? So you get pi0 into p square. Fine. So again, pi3 will be pi0 p square into pi0 again, right? Because this is your pi2. So this is pi k minus 1 would be pi0 p to the power k minus 1 into p, pi0 p to the power k. Right? You just have to multiply the p matrices and you end up getting the distributions at time k. Right? So now, since you see that there is a transformation of distributions happening, right? Whatever distribution you start from, you're going to get to some other distribution, yes or no? That is, the probability densities would change. What you can do at home is get a Markov matrix. Your homework would be sample a Markov matrix, or you can create it yourself. Matrix, write a Python code. Please upload this as well. Write a Python code or any language you like code to see how the pies change. That is, you can do a GIF of the histograms. Right? Say from 0 to 500 values of pi. So you initialize 0. So at 0, say you initialize everything to be 1 by k, equal probability uniform. Then just run the Markov chain. We'll have this discussion on the Teams, and I'll show you a theory today. But once you do the coding, you'll try to get the visualization at a particular time what is going to happen. So what my claim is that if I keep on doing this, there will come a time when pi will be equal to pi p. That is, pi k plus 1 will be equal to pi. This is my claim. I will not rigorously prove it, but I'll tell you that it exists, and it is called the stationary distribution. So it's called a stationary distribution where pi is equal to pi p. That is, if you make a transition based on the stationary distribution, you stay in the same probability distribution. Your probability distribution does not change. Is that clear to everyone? It's called a stationary distribution. As if you run the Markov chain once, or any number of times, pi does not change. Great. So now the question arises that how do you find this pi? There are two ways to find it. First is find it analytically, and then we'll find it numerically. Let's try to find it analytically first. So pi is equal to pi p. So what can I do? I'll take this to the left hand side and write this as I minus p is equal to 0. Yes or no? Here, pi is not equal to 0 and I minus p is also not equal to 0. But I'm seeing that it is becoming equal to 0. The product is becoming equal to 0. When can that happen? I'll give you an intuition. 1, 1, 1. Say you have a matrix 1, 1, 2. You have 0, 1, 1, and 3, 2, 5. If I have this matrix, can I find a pi such that this is not a pi, say a matrix A? Can I find a vector x such that this is equal to 0, which is not equal to 0? I think you did it in school, but you may have forgotten. This is called independence,
We,
right? Yeah. Go ahead.
yeah, we would find the null space.
Yeah, but I'm not taught null space. That's the reason I'm trying to say independence of rows. You can, for people who are interested, please go and see my videos from last time. I have taught all the linear algebra. You have to find the null space as Antriksh is telling me. But the intuition is you don't need to find anything here. The idea is if I just take this vector 1, 1, minus 1, that is, I add these two rows and subtract the third row, I'm going to get a matrix of a vector of zeros, right? Yes or no? 1 to 1 into 1 minus 1. So that's what I'm trying to say. What does this mean? In your school, you will learn that when this happens, what happens to this? If you find the determinant of this matrix A, this will turn out to be 0. Why will it be 0? Determinant of A? Can you tell me?
Because it's linearly dependent.
Very good. It's linearly dependent, so I can do any linear operations. This is your class 12 maths. I will do the same operation I told you, and I will get the third row to be 0. And if I as soon as one full row is 0, your determinant is 0. So what you end up doing is you calculate the determinant of I minus p and set it to 0. And this gives you the roots. So you can try some examples at home, but yeah. So the idea basically is, let's take an example, this example itself. This is not exactly a Markov matrix, but for the flavor of it. So I minus p would be something like this. I is the diagonal matrix minus 1, 0, 3, 1, 1, 2, 2, 1, 5. This would become 0, 0, minus 3, minus 1, 0, minus 2, minus 2. Where is it? Yeah, minus 2. So what you end up doing is, okay, this is going to be 0 only. But what you end up doing is you end up solving what is called the eigen equation. That is I'll come to what is it. You take a parameter lambda along with it just to solve for that. So what values do you get? Sorry, my bad. Why, I'll come to that, but it's basically this. So you solve for this determinant. So lambda minus 1, lambda minus 1, lambda minus 5, 0, 3, minus 3, minus 2, minus 1, and minus 2, minus 1. Okay, and you set it to 0. Can you tell me how many roots will this determinant have?
Equal to its rank.
So roots will be equal to the number of the size of the determinant, right? Because once you expand this determinant, you will get a polynomial of cube. Yes or no? No, rank. You'll get a third order polynomial, right?
I
You'll
should
have,
say yeah, if non-zero
yeah,
roots, then
non-zero. Correct. That is fine. Good. So this is 3 roots it will have. That's fine. So now why I was referring to lambda I is this. Say you have lambda pi is equal to pi p. What does this actually mean is, say you have rows, right? Rows. I give this intuition every time. Let me give it again this time. Pi p. What does it actually mean? Vectors. What does this mean again? What is vector that I is saying? Vector because this row is a stack of 3 numbers. Yes or no? Do you agree? In your school physics, a stack of numbers gives you a direction, right? There are 2 numbers, 1, 2. the vector again. What happens is if you have n number, it's a vector in n-dimensional space. All vectors algebra that you did in your school remains the same. So pi1 p or pi p, it actually means if pi is pi1, pi2, dot 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 pi n, and your rows are row 1, row 2, row n, you can see that this can be written as a linear combination of the rows. That is pi1 r1, pi2 r2. You can right pi n r. Yes or no? So we did that just now. That we showed that this is the linear combination of the rows, right? What do I mean by the linear combination of the rows? I mean that I multiply pi1 with the row 1, I multiply pi2 with row 2, and on, and then add the vector. Okay, fine with everyone. That's what is known as linear combination of rows. So what happens is if you take these vectors at r1, r2, r3, they're scale of that changes. The scale direction in which the direction does not change on taking a linear combination is called an eigenvector. So please go back and see this if you're interested. This is the eigenvector, and this is the eigenvalue. We are to solve it analytically, but clearly we can see that the solution for this matrix corresponds to lambda equal to 1. So you'll have to find for lambda equal to 1 eigenvector. I is the eigenvector corresponding to. It's not important for this, but if you want, please go back and see the video how to find it. I'll tell you how to find it using a computer, which you can do that I told here. Analytically, what happens for the Markov matrix, all the eigenvectors have eigenvalue less than 1. Since people are not, if you're not familiar, is everyone familiar with eigenvectors? Then I'll go and prove this.
Yes,
Everyone,
we are familiar with eigenvectors and eigenvalue calculation, analytical.
okay. So then I'll just go ahead and prove it. For what is saying is the Markov matrix, all eigenvalues are less than 1. So why? So we can prove it very simply. So you can clearly see the determinant of, I said lambda I minus a is 0, right? Fine with everybody. So now I say that, say I take a vector x and a, and I say that is equal to some lambda x. Fine with everybody. These are row vectors. Normally people don't write row vectors, but we are doing row vectors here because of in probability people like statistics, they like writing row vectors. Okay, so now I tell say x is equal to x1, x2 dot 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 xn. I say xj is greater than all xi's or all i's. Fine with everybody. I say that a j index is greater than all I indices. So for that j index, what can I write? Lambda xj can be written as, can you tell me? If I write it down x1, x2, xn, and A matrix is A11, A12 dot 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 A1n, and so on. And then let me write P only. P matrix, P11, because it's the Markov matrix, it's a special matrix. P1n and so on. Pn1 dot 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 P nn. So what is it going to be? The jth value, jth lambda value. That is the jth column, yes or no? Tell me. So this is going to be sum over all i's Pij. Where is it? Sum over all i's. Yeah. Is this fine with everyone? Here. I just wrote the ith index. So x1, x2, dot, 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 xn. Here there is an xj. I am writing it to it x1, x2, dot, 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 xn into P matrix. And I'm writing out this term, this xj term. And that is turning out to be this. Is this fine with everyone?
Yes.
So now if I take mod on both sides, what do I get? J equal to or I equal to 1 to n Pij xi. I get mod lambda mod xj is, what is it? Less than summation of Pij xi, I equal to 1 to n. Can you tell me how I wrote this? Very simple, but think about it. So let me show you how I wrote this.
Like triangle.
It's a triangle inequality, very good. But people who just, this is, you can just clearly write this. So x mod x is more than x, y mod y is more than y. So x plus y mod y plus mod x is greater. Similarly, minus x say minus mod x minus y minus mod y minus x minus y, so x plus y. Fine. So what I say is your individual sums. So you can go for, if both of these are true, then x plus y mod, it has to be less than mod x plus mod y. This is the triangle inequality proof. Okay, fine. So now what can I do? I can again take an upper bound on this. I equal to 1 to n. Can you tell me what I'll do? I'll replace this as xj. Yes or no? Because xj is greater than for all xi. That's the assumption that I took. Fine. So I just cut xj's from both sides. And this is 1. Yes or no? The sum over all the row elements as we have defined for a Markov matrix. So lambda value has to be less than 1 for the matrix. Okay. These are equal to operations again. So 1 is the one that the lambda equal to 1 is what you want to find out, find it for. Fine. So now why did I prove this?
Can't hear you.
So, I mean,
Yeah, but a little like low.
now, here. Can you hear me now?
Yes.
Okay.
Yes.
So everything till that point was audible, or do I need to say something? That all the lambdas have to be less than equal to 1? That you heard, right? All the eigenvalues have to be less than equal to 1 for a Markov matrix. Now I tell you, if there exists only one lambda equal to 1, then I can get a, starting from any vector, I can get to this. Can you tell me how? Say I start arbitrarily at pi 0, right? So pi 0, do you agree, can be written as a linear combination of all the, say, Ci's into, say, the eigen, so for this P matrix, as you know, it will have how many eigenvectors if it is if you can do an eigen decomposition? It will have
Equal to
vector
yeah.
equal to n. Rank also, that is also true, but also you can have null space vectors as well. So let us consider full rank, whatever is going to be. It will have the same number of eigenvectors, because null space vectors are at the end of the day eigenvectors only.
Yeah, eigenvalue can be 0. Yeah.
Yeah, exactly. So this is like V of them. So in your school days, do you agree that any vector, if you have two independent vector, you can represent in R2 any vector using them, say this, by sum alpha1 V1 plus alpha2 V2. If this is V1, this is V2. So similarly, you can also do it for any vector pi 0 using the eigen variables. I did this in details in my course. Please, if you're not familiar, please go back and see. Pn Vn. This is what you can write this as for any arbitrary V. So now what I do is I multiply P on both sides. Right? This will help me a lot because C of, say, V1 is the matrix which is corresponding to lambda 1. These are all less than 1. So you will get P, the V, what is V1 P1? That is, for our case, is pi. The other this is equal to pi. What is pi V? That is equal to, size pi P is just P, pi. Yes or no? Pi P is just going to be pi because that's the solution we are looking for. The
Yes.
other one will be C2 lambda 1 lambda 2 V2 because I know V2 P is equal to lambda 2 V2. Similarly, I go on Cn lambda n Vn. I keep doing it for lambda not p to the power k. What will you get? You get C py pi plus C2 lambda 2 to the power k V2 dot Cn lambda n to the power k Vn. Yes or no? This is what you will get because I'm going to multiply p at every step. Again, I'll multiply p to get pi 0 p square. Yes or no? And I go on doing it for k. So these terms all go to 0 because as limit k tends to infinity. Only this remains. So it becomes just some constant times the eigenvector. So you can just rescale it. So you start from any pi 0, keep multiplying p, you will get the eigenvector vector corresponding to 1. That is only for Markov matrices, not for any other arbitrary matrix. Okay, fine. Any questions? I'll only have time for one question. Please do the second question as homework. I did it last in my previous course. You can also go back and look at it. Let's see some properties of this Markov matrix. So the property that I just discussed now is the pi exists if, say, there's a path from every state to every state. If you have a path to go from every state to every state, if every state is reachable and no subgraphs are made, pi is unique. This is one property. That is, they are numerically stable. You can get a numerically stable solution. And the last property, which is very interesting, Sadly, I don't have time to do it. If it was a probability course, I would have spent like 3 classes to show that. But this is the most interesting property of a Markov chain. In a Markov chain, say, if you let the Markov chain run long enough, right? If you read the Markov chain run long enough and you record the time, say you start from state I and you see record average time to return to I, that is exactly equal to, that is, say you define this as some time Ti, then 1 by Ti is the probability, that is the stationary distribution's probability. Isn't this so interesting? So it's like, say it takes on average 4 steps to return. Example, 4 steps to return. Then in the stationary distribution, pi y of I will be 1 by 4 is equal to 0.25. So this is again this is exactly what we discussed just now. I think that it's just an extension to that proof where we see that it's like you keep running the Markov process and you keep seeing how much time is it taking to return to that state. And on average, if you take all the averages, you will see that it is equal to the stationary distribution. So this is another way of analytically finding. So write these two codes down. So you can use both the methods, analytically finding. So one method would be to use a random initialization and go on iterating over pi. And other one would be to keep on going over pi. And that is again from a random initialization and see on average what is the percentage of time it takes to return to a particular state. Okay, any questions, any doubts before I go to the last question of the day? Anything you want a clarity on? Okay, so let's take an example. This is an interesting question, which says that till now we did a random walk where it was 0, 1. So now I say that xi is a map from the sample space to -1, 1. Right? So that is at every state, if you had a Sn is the random walk, what can happen? You can either go to next state with probability p. So I'm saying probability of xi equal to 1 is equal to p, and probability of xi equal to -1 is equal to 1 minus p. Right? So say this is k minus 1, this is k. Is this fine with for the random walk? Fine. Okay. So now I define another process, Mn, as the max of Sk between 0 to n. Right? Can you tell me, can anyone give me the intuition of this process? This process Mn. I will draw that. Do you agree? This is the maximum state you ever went to. Right? Maximum n up to time, whatever time you are, that is n. Yes or no? If you are looking for at time n, what is the maximum Sn you have observed? Is this fine? Say at time n, since you can go negative also, you were here somewhere. This is your Sn. But your Mn can be somewhere here, right? Because say something like this happened. You went positive, 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 positive. But now you went back. Correct? Currently, you are here. Fine with everybody?
Yes.
So now this, we are told to show that this process Yn as Mn minus Sn is a Markov chain. Any idea how will I show it? See, whenever that's a question, it's difficult. You try to say this, assume this to be small y. So the probability that Yn plus 1, the case 1, I'll take two cases. Case 1, Yn is not equal to 0. Do you agree? What value Yn take first? Tell me. Negative. Do you agree? Yn is always greater than or equal to 0? Because this is the distance from the current state to the maximum that you have seen till now. Yes or no?
Yes.
Distance from current state to maximum observed state. It's always positive. So I say it's not 0. So I will ask you. So now, if this is take y steps away, this is y steps away. So I'm you yn minus 1, this was at y steps away. What are the two outcomes is it possible? So what are the probabilities that is possible? Yn plus 1 or probability Yn is equal to Yn minus 1. Yes or no? These are the two probabilities only that can happen. This happens if you with one p probability and you move forward with probability p. This step is 1 y minus 1. This is y plus 1. Yes or no? Right? This happens then. This happens with probability p, and this happens with probability 1 minus p. Yes or no?
I think you wrote like reverse. When it would be 1 minus p for y minus 1, right?
Y minus 1 is when you take a positive state, isn't it? So y minus 1. So this is
Oh,
your
sorry.
Sn. Yeah. No problem. You at least understanding that's the best thing. At Yn minus 1, if you take a positive state, your distance reduces. That is Mn minus 1 minus Mn minus Sn will become Yn minus 1. So it just depends on the current state. Does not depend on Yn minus 2. It does not depend on it at all. Given, of course, given Yn minus 1. If it was not given, then it would depend. Now, if Yn equal to 0, what will happen? What is the probability it stays at 0? Can you tell me? Say currently your state Mn and Yn, that is Mn is equal to Sn. That is the case when your Yn is equal to 0. Yes or no? Yes or no? This is fine.
Yes.
So now I say that it stays at 0 only when you have a positive p. Yes or no? So then this goes in this
Yes.
case. So Mn again becomes this Mn equal to Sn and Yn stays 0. So and with 1 minus p, it can go to the minus 1. So this is with probability p, it stays in 0 and probability of it goes to minus 1 or rather 1 with probability of 1 minus p. So if in the second part of this question, I ask you to draw the transition diagrams. So states are 0, 1, 2, dot, dot, dot. 0 to 0 is with probability p. 0 to 1 is with probability 1 minus p. 1 minus p. 1 minus p. Dot, dot, dot. And you come back to a lower state with probability P. Is this fine with everyone? Any questions? Fine. I have time for some questions. Please go ahead and ask if you want.
Could you explain the last property here that you showed? The last property of Markov matrices.
Okay. That is the Markov matrix. That is like the average return time is same as your stationary distribution. That's what, right?
Yeah.
Okay. So what you're trying to, so the proof is like 3 lectures long. So I'm not going into the proof, but I'll give you an idea. Say you start from state I. Start from state I. You go around the entire graph and return to state I, right? This is your return time. This is called a return time. Return time. People say that it is Ri or Ti, right? For every state, you will have a return time. Yes or no? Say 5. So
Yes.
say from I you went to 1, then you went to 2, then you went to 5, then you went to 7, and then you went back. So 1, 2, 3, 4, 5. So in this case, your Ri 1, 2, 3, 4, 5. Yeah. So Ri for this trajectory was equal to trajectory I or whatever trajectory star trajectory is say 5, right? Similarly, there can be multiple other trajectories. If you run the Markov chain multiple times. So next time you came back in 3 steps, right? Next time you came back in larger number of steps, say 9 steps. So what you do is you take the average of all the return times, number of times by n, whatever number of times you return, right? Average. This is in expectation by law of large numbers. Law of large numbers. This will give you the expected reward return time of state I. Yes or no?
Yes.
Law of large numbers. So this will give you expected reward time of large numbers. Law of large numbers. So what it says that is that the expected return time Pi is the same as the stationary distribution of that. The probability of stationary distribution of that state. Is that fine? So the average time to return to a state is same as sampling from a Markov chain or sampling from a multinomial distribution with probability pi I. That is, you start from this 1, 2, dot, 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 n. If you just sampled the state I with according to this distribution pi, only pi, say pi is 0.2, so only 20% of the times will you get pi, right? If you just sample from this distribution, say you have the distribution 0.1, 0.2, 0.3, and 0.4. So if you just sample, if you're interested in state 1, if you keep sampling based on this distribution, so you will have 20% of the times your state 1 will be selected, right? Yes or no? Correct? If this is your stationary distribution. Antrix, fine?
Could you just say what you said? Nine.
So I'm trying to say is, so if you have a stationary, if you have a distribution and I sample from the distribution, right? Sampling means just say if you sampling from a Bernoulli distribution is like tossing a coin. So say 1.1, 0.2, 0.3, and 0.4. 0.1, 0.2, 0.3, 0.4. So I'm saying this means that 20% of the time state 1 is selected. Yes or no? Just if you sample blindly, no Markov chain is being done here.
Yeah.
Fine?
Yeah, man.
Now,
You index like 0, 1, 2, 3, 4, right?
Yes. 1, 2, 3, 4. Now I tell you this, the expected return time to state I, that expected return time to state I is just going to be 1 by P. That is 1 by 0.2. That is your 5. So it is like how fast you will return to a state depends on how probable is it likely, how probable it is to sample from that distribution. So whenever you see computers sample from a distribution, they're actually sampling from the Markov chain. They build a Markov chain with this stationary distribution and walk on that Markov chain to sample. Do you understand the analogous thing?
What I just couldn't.
So what I'm trying to say is, say state 2 will be selected 20% of the times, yes or no?
Yeah, state 2 would be selected 20%.
The property says that the return time to state 2 is just 1 by P. That's what we
Yeah,
mentioned in
that's
the property.
yeah, that's all.
That Yeah, so you will return to that state in 5 steps, yes or no?
Yes.
So now if I run this chain, so you will return to this in 5 steps. You will return to this in 10 steps. You return to this in 10 by 3 steps. So you return to this step in 2.5 steps, right?
Yes.
So now if I just take this Markov chain that I have, if I construct this underlying Markov chain which has this and this condition, this distribution. So I say I construct this Markov chain. Say I have a Markov chain 0, 1, 2, 3. I'm not constructing the exact one, but say this is the Markov chain that is being constructed. And I start from any state and I just follow the transition distributions as I was doing in the previous one. I'm saying I will be sampling from pi. Because on average, you're returning to that state in the same proportion of the times as is the probability of the stationary distribution. Yes or no?
Yes.
That's the interesting property that the computers use to sample. Okay. So we'll stop here. Please do this second homework. It will help you. The interesting problem. And if you're not able to, please go back and see my previous sessions. I'll give the link of that as well. And try to write down the 2 codes. We'll see you next day on Monday. I'll stop recording.